Hi everyone, my name is Li Jiahui. We are from Group 12. Today we are going to present the short-route small aircraft. They are our group members, Muhammad Yunus, Abarawi Said, and also Fa'an. So we will go through research of aircraft, engine selection, thrust-to-weight ratio, distance covered during climbing and landing, mission profile, basic parameters, takeoff mass estimation, wing loading, high lift devices, wing design, tail design, fuselage design, propulsion system, landing gear, electrical system, materials and fabrication of structural components, operational consideration, and lastly, market research. The research of aircraft. We did research of 5 aircraft from small size to medium size. After the research, we chose a suitable engine for our aircraft. The engine we chose is 4-engine turboprop. Turboprop aircraft the best suited for short-haul flight because of its higher efficiency for short distance. Turboprop excel at fuel efficiency at low altitude. Turboprop aircraft also be able to take off and land on shorter runways, so it is suitable to small airports. However, turboprop aircraft have a limited cruising altitude, which from 25,000 feet to 30,000 feet. The third part is the thrust-to-weight ratio. Thrust-to-weight ratio for popular aircraft at sea level is 0.17741. So now we are going to show distance covered during climbing and landing. The maximum climb angle is 6.6223 degrees, so that the distance covered during climbing is 215,000 feet, and the distance covered during landing is 477,000 feet as 3 degrees of descending. The cruising range of the aircraft from KLIA to Senai Airport is 357,000 feet. Now we are going to show the mission profile. First, the aircraft warm up and taxi for 10 minutes. Later, we will take off and climb to cruise altitude, reach 25,000 feet. Later, it will descend to sea level, which range credit. After that, it will climb back to 3,000 feet and loiter a best endurance speed for 45 minutes and descend to sea level with no loiter time credit. And lastly, we will landing, taxi, and shut down in 10 minutes. There are few basic parameters in our calculations. The total capacity is 40 passengers, while the mission capacity from KLIA to Senai Airport is 20 passengers, with 50% of total passengers. The engine type is 4 turboprop engines. The maximum lift-to-drag ratio is 16. The cruising speed is 0.75 Mach numbers. The stall velocity is 61 knots, and the zero lift-drag coefficient is 0.015. The takeoff mass estimation. 6% of fuel will be researched. There are some estimation from part 1, warm-up, taxi, and takeoff. Part 2, climb. Part 3, cruise. Part 4 is climb again. Part 5 is loiter. Part 6 is landing. So the ratio of part 6 to part 0 is 0.90195. So the ratio of fuel weight to maximum takeoff weight is 0.10393. Lastly, for single pilot, 1 flight attendant, and 20 passengers, the maximum takeoff weight is 6,560 kg. 8. The wing loading. We calculate the wing loading for takeoff condition, for stall condition, for landing condition, for cruising condition at maximum range, for cruising condition at maximum loiter, and lastly for sustained turn condition. The lowest wing loading should be chosen to guarantee that the wing provides appropriate lift. The lowest wing loading is wing loading at stall condition, which is 10.17. The wing loading of stall is the lowest, then the wing should be equipped with a high lift device. So with high lift devices, we choose leading edge slate. The flow separation causes a stall. Flow separation usually occurs in the face of strong adverse point gradients along the surface, so as downstream or minimum pressure point on an airport at high angle of attack. So it will provide additional 0.35 of lift coefficient when deflected. The 10 is the wing design. Before that, we do some recall about the maximum takeoff weight is 6,560 kg. The wing surface area is 55 meters square. The cruise speed is 0.75 Mach numbers, and the stall velocity is 61 knots. So for ideal lift coefficient, the ideal lift coefficient is 0.092344, while the maximum lift coefficient is 1.9191. The following airfoil is matched with the design requirements, which is NACA 64112. Now we'll go to the flight parameters. The takeoff speed of aircraft is about 10% faster than the stall speed. So the takeoff speed is 34.519 meters per second. The lift coefficient during takeoff is 1.6034. There are some few values for flight span, flight corp, angle of attack of wing during takeoff, and flight direction for takeoff operation. The wing lift coefficient while the flight is deflected during the takeoff operation is calculated using MATLAB. However, the value we calculated using MATLAB is slightly lower than the value required takeoff lift coefficient. So the wing angle of attack during takeoff is increased to 13.6 degrees. The setting angle is 2 degrees. So there are some calculations for other parameters, which are wingspan, maximum aerodynamic corp, root corp, tip corp, flight span, and also flight corp. So we can see that the length for root corp is 3.05 meters, while the length for tip corp is 2.14 meters. The maximum aerodynamic corp is 2.62 meters. The flight corp is 0.5244 meters, while the half of the flight span is 6.293 meters. The half of the total span of the wing is 10.488 meters. This is the side view of the aircraft. The setting angle is 2 degrees. The takeoff angle for wing is 13.6 degrees, while the takeoff angle for fuselage is 11.6 degrees.
Hello everyone, my name is Farhan Abrahan and my matrix number is 204801. So I'll be doing the tail design, and for the tail design we'll be needing these equations that are shown in the slides. So these equations are the most important ones. Over here we have 6 equations, and then lastly we find the fuselage length. And then we go over here, we find these values. Over here, I'm just showing the equations, the proper calculations, and the answers. The calculations are given in the report, but the answers will be given down in a table altogether. So over here we have 5 to 6 values given to use them in these equations below. Then afterwards we find these values, and lastly by finding this value we can know that this airfoil is NACA 0009. So then we use these are the most important equations, and we find these parameters and we use this last equation. So all of this is given in this table. All of these values were calculated in the report, and over here you can just see the answers. So, and lastly, from all these answers we have come to this design. Over here you can see the length and the MAC and the CH deep and the breadth and everything. So this is our final tail design. Thank you very much. That's all from me, and I'll let my friend continue the presentation.
Okay, I'm going to continue with the fuselage design. So from the design requirement is a civil subsonic turboprop aircraft. Number of crew is 1 and 1 pilot. Total, which will be 42. Fuselage configuration is a single deck. Number of doors is 1 passenger door and 1 overwing emergency exit, and the length to diameter ratio optimum is 16.3. So the possible configuration for our seats are shown here, and from the width of the cabin formula, we can get NS is the number of seat in one row, WS is the width of the seat, NA is the number of aisle, WA is the width of the aisle. So we can get the diameter of the fuselage by calculating the weight of the cabin and increasing the thickness of the walls. Length of the cabin can be calculated from this formula, where we include the length of the nose, the cockpit, the cabin, the rear end, and the toilet together with the galley. So the fuselage design are all calculated, and the optimum one is selected to be 3 seats in one row with a total of 40 seats, and the length to diameter ratio is 10.6. The volume required for storage, for fuel storage, is calculated here by using the MF to the M0 ratio in the TOGW calculation, and we get the volume of fuel to be 0.87982. And this fuel is combined with the volume of the cargo, and we can calculate if the volume is sufficient or not from the volume of the total cabin. So for the fuselage and rear section, fuselage rear section and the absolute angle, so we select the initial rear length to be 1.8, and the angle of the cone is 26.89, but it seems that it is much higher than the suggested one. So we are going to select an absolute angle of 20 degrees, and the length of the rear end is updated to be 2.5 rather than 1.8. Hence, the length of the fuselage is moderated. Thank you. Assalamu alaikum warahmatullahi wabarakatuh. My name is Said Hafiz Said, matric number 204716, and I'm going to continue with the presentation with the propulsion system for our aircraft. For our aircraft, we selected the turboprop engine because it's easy to maintain and cheap compared to turbofan and turbojet, and it has less noise pollution compared to the piston engine. And from that, we are going to calculate the engine thrust and the power required during cruise. So from the formula of the coefficient of lift, the K, we can get the coefficient of drag. And from the coefficient of drag, we are able to get the D, which is the drag force. And since for aircraft to fly, the thrust must be equal to the drag force. Hence, we get the thrust force to be 12478 Newton. And from that, we can calculate the power of the engine if we have the velocity of cruise and the efficiency of the engine. Both value we have, and we can get the power required during cruise. And from the power required during cruise, we can get the power required at sea level, and both values are displayed here, 485.8.1 and 12717 horsepower. And the diameter of propeller and the propeller rotational speed can be calculated from the formula of the diameter of the propeller. We can get all the values, the aspect ratio of the propeller, the efficiency of the propeller, and the power. And from that, we can get the W, which is the rotational speed, and we can get the number of revolution per minute N from the formula of 60 rotational speed over 2 pi. And lastly, from the data of the power required, we can select our engine. So our engine is selected is the Rolls-Royce AE2100C. That's the propulsion. Thank you.
So I'll be presenting about the landing gear, electrical systems, and materials used on the aircraft. The landing gear of the aircraft is designed as a tricycle. Aft of the tricycle's center of gravity are the two main landing gears, and at the nose, an auxiliary gear. Due to the location of the primary gears, this layout is very stable because it is very close to the center of gravity. Due to the configuration of the tricycle, the aircraft is also easy to maneuver and taxi. Compared to a tail wheel landing gear configuration or tail dragger, the tricycle configuration also provides better view over the nose of the aircraft and a flat cabin floor for better movement of passengers and goods. Next is the electrical systems. For a turboprop aircraft, there is a starter for each engine, and at least one battery that provides electricity to a 28-volt DC electrical system. The generator starts the engine using electrical power, and after the engine gets going, the rotation of the engine generates electricity in the form of direct current, which is then converted into 400 Hz AC to be used for certain equipment on the aircraft, such as avionics or lights. In order to prioritize certain equipment, the power distribution is organized into buses. Most of the aircraft's electrical system is served by the main buses. There are also current limiters to protect the buses from issues such as short-circuiting. Next is the materials and fabrication of structural components. So when choosing materials for an aircraft, there are a few main considerations to be made, such as strength, weight, stiffness, toughness, fatigue resistance, and corrosion resistance. Some of the materials used in the aircraft include aluminum alloy, which is used to produce airframe, skin, and other stress components, steel, which is used to produce fasteners, wing root attachment, or tracks, titanium used for access doors or as shear for areas of hot gas impingement, and carbon fiber reinforced plastic or CFRP for the wing, tailplane, and front fuselage. So fabrication of structural components. So for the wing, thin aluminum alloy web and flanges are extruded, machined, and bolted or riveted to the web and make up the spar of wing designs. The ribs are manufactured from sheet metal in 3 pieces. For the skin, longitudinal stiffness and rib flanges are riveted to the skin. Since aerodynamics is important in the front chordwise regions of the wing, it has to be very smooth, and therefore countersunk rivets are used as opposed to dome-headed rivets, since countersunk rivets are flat when they have been riveted onto the wing. And lastly, stiffening of flying control surfaces. So a sandwich panel is a type of construction that has thin corrugated metal or a honeycomb structure core, which is sandwiched between 2 outer skins of a stress-bearing sheet. Sandwich panels feature smooth interior and exterior surfaces and can withstand high loads.
Now I'm going to present the operational considerations. According to Chapter 15 in Airplane Flying Air Book, turboprop propeller power airplanes, the engine will face some difficulties. The first one is the split shaft or free turbine engine's power output delays for many seconds when the pilot switches the power level from flight idles to a high power levels. The second, the turbine engine heat sensitivity is a further factor for pilots who are making the shift. Next, I will show the takeoff and departure for turboprop. The takeoff and departure profile must adhere to the recommendation of the aircraft manufacturer as stated in the Federal Aviation Administration Approved Pilot Operation Handbook and or airplane flight manuals. The pilot should predict an increase in engine temperature as altitude rises at constant power for any given high horsepower operations. So the figure shows the mission profile for takeoff and departure. And the second part is the arrival and landing. The approach and landing process must start with a stable approach. In a stabilized approach, the aircraft is placed in a stable descent on a glide path that ranges from 2.5 to 3.5 degrees. So the figure shows the mission profile for arrival and landing.
Okay, I'm going to talk about the market analysis. So our proposed route is Kuala Lumpur to Johor, and the proposed passenger 40 passenger, and different mode of transport are calculated here. So for the aircraft, the time is 1 hour and the distance is 295 kilometer, and we can get possible route of 4 routes, and the cost per for passenger is 70. For car is 3 hours, and the cost is 80 ringgit. For the bus, it is 4 hours, and the cost is 38 ringgit, and the train is 30 ringgit. So From this, we can see the different advantages and disadvantages of using different modes of transport. Like the aircraft, it is fast and you can get possible routes of 4 per day. And the the bus and the train takes more time, while the bus and the train, the cost is less compared to aircraft and car. So by taking into account the disadvantage and the advantage, we can conclude that it is feasible to set the Johor to Kuala Lumpur route because the cost is not too high and the time taken is only 1 hour. And we are going to consider further in the report the cost for the fuel and the labor in aircraft and form a good structure on how to run the airline. Thank you.